Does that make sense? One was the diene, the other was the dienophile. We only used one alkene of the other molecule, right? Diels-Alder's 4 plus 2. It ain't 4 plus 4. 4 plus 2. 6 member ring. Did we get it? Hopefully that was useful. Okay, guys, let's get started. We have Mass Spec that we can continue on. Then we need to get to the, hopefully, into substitution today. And you should have that handout printed out from what I sent you by email. We'll get back to where we were. Who's first person to make a mass spectrometer? Back about 1900, 1905. He also discovered the electron. Who was it? J.J. Thompson, yeah. How did he discover the electron? Well, he was dealing with some type of electromagnetic radiation. He observed that it was bent by a magnetic field. It turned out that it was the electron. I reckon they rationalized, well, if we can do this with subatomic particles, can we do this with like an entire molecule? Eventually they were able to do it. Accelerate it through a magnetic field, let it get bent, somehow calibrate it. Again, a lot of ingenuity goes into calibrating that to make it the degree of bending correlate to the mass. Yeah, J.J. Thompson built the first mass spec. Where did we leave off at? Which compound? Ether, amine? Like, which compound did we leave off at? We do aromatics, amines?
We just finished purple amine.
Anybody? The primary amine? Okay.
You're right.
Start right here. I assume we did the amine. The previous ones we made cation. Where do you want to get cation when you cleave in mass spec?
Resonance stabilized.
Or make resonance stabilized if you can. Or remember what we were going to look back at the other one and we're going to see where the cation we can make. Where can we cleave? Did we do this one? We did this one?
Yeah, we did.
You said where we would cleave.
Okay, if we cleave here, what do we get? Why would we do this? We want to cleave where? Next to a lone pair?
Yep.
Why do we want to cleave next to a lone pair?
Resonance.
So we can do resonance. Okay, I'm not going to draw the resonance structure. You should be able to draw a resonance structure. This is what? M minus what? M minus 15. We cleave the methyl. The mass is 101. 101 minus 15 would be what? 86. Do we have an 86 on the spectrum? It's there, it's small. 86, M minus 15, right? That would be the cation. This cation here. Where else could we cleave? That's called alpha cleavage. Cleave to make a cation next to a lone pair. Or we'll cleave to make a cation next to a pi bond. Basically, we'll cleave to give a resonance stabilized cation. Where else could you do so-called alpha cleavage here? We cleaved here, we would get this cation plus the tertiary radical. This would be M minus this. That's C4H9, 48, 9, 57, M minus 57. I think that's right. 101 minus 57 would be what? 44? Do we have a peak at 44?
Yes.
Is this 44?
Yes.
Well, that's what I drew there. Yeah, it should be. It's 44. That turns out to be the base peak. Why is it more prone to cleave there? They're both resonance stabilized cations. We can look at the radical. That's a tertiary radical. Over here we form what? It's really not even primary. That's a methyl. Just a methyl is not even considered primary. Ethyl would be a primary. We can also cleave here. Could you envision cleaving here, and instead of putting radical here, put cation here? Yeah, you can also envision putting cation here and radical over here. And this would be, it's probably easier not to do M. It's probably easier just to say, well, that's the same mass as that. It's 57, isn't it?
Yeah.
Do we have a peak of 57?
Tiny one. Very tiny.
Very tiny, so that wasn't that major. Apparently it liked to cleave to make this here, resonance stabilized cation. Okay, I'm assuming everybody can do resonance now. So resonance structures here. On the next page we have some aromatics. So-called alpha cleavage here, we will cleave between the first and second carbon coming off. And we're going to put cation where? On the carbon adjacent to the ring. This is called, remember what that position is called? Benzylic cation. Why is this a good cation? Because it's resonance stabilized by the benzene ring. This is resonance stabilized benzylic cation. We did resonance of that when we were looking at resonance. You should, of course, know how to do resonance of that. So what did it lose? That's M minus 29. Mass is what? 120? 120 minus 29 is what? 91? So hopefully that peak there, which is the base peak, 91? Yeah. Molecular ion is here. What's 121? That's where one of the molecules, some of the molecules have a C13 in them. Everybody knows 1% of the carbons in your body are C13, right? Well, 1% of the carbons in this sample of this compound are C13. And so if you look at chance, there's a good chance that there's one carbon in this molecule that's C13. There's probably also some molecules that have two carbons that are C13. That's maybe something here. It depends on how sensitive your mass spec is. What's the chance of all of them being C13? I mean, very, very low, but there's probably a molecule out there that's like that, just from chance when you get up into the gazillions of molecules. But it'll take a very sensitive mass spec to see all the possibilities of how many C13s. So that is propylbenzene. Below we have an isomer with an alpha and a methyl, same mass, 120. So we also see 120, but here the base peak is at M minus 15? Because it's at 105. 120 minus 15 is 105. That means it lost 15. Well, it cleaves at the same place. Where does it cleave? It cleaves to leave a benzylic cation. So you cleave here, and you give that minus what? CH3 radical. Just lose the CH3 on the end, which is 15. What you're not going to do is cleave between the ring and a carbon. I know it's going to blow your mind, but that is not a resonance stabilized cation. If you think about it, it's not. And if you draw your orbitals, this has 6 p orbitals all overlapping. This empty p orbital here is perpendicular to the other 6. This is not good, but that is good. These 6, then you can put this 7th one overlapping with these 6, and that's what we did with resonance there. So 2 isomers, the mass specs are very different. One shows M minus 15, one shows M minus 29. And so that's that illustrates what we're predicting here. Benzylic cations. And so if you had a sample of a compound and you were told it's one of these, all you have to do is run Mass Spec and see which one is which. Because you know what to expect. Okay. Not really any other major peaks there to predict on either one. Okay, let's look at carbonyl containing compound. There's a ketone here, mass. Don't look, is the mass odd or even? Just look at the structure. No nitrogen, so it's even. Okay? 86. We do have a molecular ion here at 86. Base peak, already shown structure over there. Okay, where do you want to cleave to make a cation? Resonance stabilized. And with carbonyls, the important is next to a lone pair. So where do you want to cleave? We can cleave here and put cation. There's one structure here. I'll go ahead and draw it. It may already be there. Put cation here, plus a CH3 radical. Why there? Next to a lone pair. This looks a little funny. This is resonance stabilized. This is sort of the, remember back when we said anytime a lone pair is next to a p orbital, I don't want to be in a p orbital. Some of you ask about the SP, and I usually said, well, it's only going to happen when it's sp2. But this is a case where it's not. What's the hybridization of oxygen there? This oxygen is sp. Anytime a lone pair is next to a p orbital, it can only be in a p orbital. This oxygen is sp. We can show a resonance structure. We can move these down. If we move that down, what do we get? Show what that gives. How many bonds between carbon and oxygen now? 3. How many lone pairs remaining on oxygen? Only 1. Where's the charge? the oxygen. There you go. It looks SP now, right? Linear? Yeah, it's SP. What's the geometry of this carbon here? Yeah, it's also SP. See right here, that's the incorrect geometry. It's SP2 there. It's actually SP now. And I got the geometry actually wrong there. I'll do the geometry correct over there. You have to think about this structure. You got the original pi bond. Then you got an empty p orbital. The oxygen lone pair can interact with that. So you got the original pi bond, plus you also got the oxygen lone pair interacting with the empty p orbital, and it's perpendicular to that other plane. Which one's major? This is two resonance structures. Which one's major? Did you say the linear one?
Yeah.
They're both linear.
One that looks linear.
Okay. Yeah. I didn't draw this correctly. Whenever you do resonance structures, you don't change any geometry or anything. It's really just one structure. Right? Major because there's more bonds. Okay? This cation here is called the acylium ion. You may see it like this, or a lot of times books will just directly show the major resonance structure. Acylium ion is your favorite ion produced from carbonyl compounds, particularly aldehydes and ketones. We lost 15, so this is M minus 15. So we got 86 minus 15 equals what, 71? Do we have a peak at 71?
Yes.
Yeah, I already had the structure there. See, we can also cleave on the other side. If we cleave on the other side, we get that acylium ion. We cleave over here, we get rid of all that and just make this acylium ion. You can show resonance structure of that. That's apparently the more favored cleavage, because here you get that plus what? That's a primary radical. That's more stable than just a plain methyl radical, because at least this radical has a donating carbon attached to it. Remember, radicals are stabilized just like carbocations. Donation by carbon groups. They're electron poor. Question?
What if could you cleave between the 2 and 3 carbon on that chain?
Here?
Yeah.
Well, you could, I mean, but that's not going to give you a resonance stabilized cation. That would give you maybe this radical and this cation. Something like that. Can you draw the resonance of that? You don't want to do this, do you? And leave that oxygen with no octet? That oxygen will get mad at you. That's not a good cation. Not a good cation. But putting the cation there is good because you get this resonance stabilization here, acylium. You have to just look at that structure. The acylium is a very stable cation. We'll actually form acylium ions in organic 2 during some reactions. Here we just see it in Mass Spec. Below we have an isomer, also 86. We'll talk about Nucleophilic in a minute. Now this is a symmetrical ketone here. If you cleave over here, you get that. If you cleave over here, you get that. It's the same thing, hopefully you see. Either way, you get this. For example, you get that with loss of the ethyl, loss of 29. So this is M minus 29. That'd be what, 57? Is that tall peak 57? Yeah. It's also a 29 there. It's odd, but that's apparently where it cleaved, and for some reason it put the cation on the ethyl. That's very odd, and we would not predict that. It's quite high. It's very surprising that the 29 peak is so tall. The only thing I can see for a 29 is just an ethyl radical, or I mean an ethyl cation. There's no resonance there, so. But you see the two ketones, they have very different mass specs if you think about what you expect from acylium ion formation. If you were given these two compounds and then showed the two mass specs, you would be able to match them up. You look at your structure, you predict what fragments you expect, what acyliums you expect to form. At the top, you expect two different acyliums. On the bottom, you expect really only one, and it's different from the two at the top. On McLafferty, I'm not going to mention much here. In your group report, you are asked to discuss the McLafferty rearrangement of your product you made in lab. McLafferty is it's a rearrangement of carbonyl compounds in the mass spec. I forgot who discovered it. It's a rearrangement. It's not it is a cleavage, but the molecular ion is a radical cation. And usually when we cleave, we get a radical and a cation. They separate. In the McLafferty, your product is still a radical cation. And what you cleave is a neutral molecule. Because of that, you get a different molecular weight for McLafferty compared to ions. See, this is just a plain ion. McLafferty is a radical ion or cation. So basically, if it's a radical cation, it's going to have a different molecular weight from your plain cations in terms of odd or even. So one way to pick out McLafferty is you start it even, it's also even, where your other ions are going to be odd. But I want you to look in your textbook and figure out the McLafferty on your own, and you're asked to include that in your report for your product. It's made from the hexane hydration. One requirement from the McLafferty rearrangement to take place is you have to have a gamma hydrogen in your compound. Okay. The first carbon coming off from the ketone is called alpha. Second one's beta. Third one's gamma. And there is an H there. There's actually three there. So this compound has a gamma hydrogen. It can do the McLafferty. Does this one have a gamma hydrogen? No. No, you're not going to expect a McLafferty from that one down there. And so that's why I say no McLafferty possible. Okay, we looked at mass spec of major compounds to consider. Where do you want to make cation at typically? Next to a lone pair or next to a pi bond, like in a benzylic. Okay. In both cases, they'll be resonance stabilized. If there's no possibility of resonance, you're going to probably cleave to get like a tertiary cation or a secondary, or there's nothing possible. You have to be primary. You can do primary cations in mass spec. Mass spec's pretty high energy. Let's look at the back at the very first page or the second page, where we have the two alcohols. We need to make sure we can do mass alpha cleavage of alcohol. Pull this down. Where do you want to make cation? Yeah, so cleave here to get that cation resonance stabilized, right? That's probably what I got drawn right there, right? Is that it? Yeah. And what's the mass of that? If you add it up, it's 31. So base P. Cleave where you're supposed to cleave. About the one below, the other alcohol. If you cleave here, you put cation here, radical there. Cation here would be not that. Be that, wouldn't it? You cleave over the cation there. See, next to a lone pair. That's that peak here. So you can cleave over here, right? Leave this off and make the cation I got shown. That's there. That happens to be the base peak. So those are the two you would predict. That mass spectrum has it. If you look right above, you can, I think they're lined up, but the one above doesn't have these two peaks. It has the other peak because it's a different structure and a different alpha cleavage expectation. So you see how you expect different mass specs for the two alcohols? Are you convinced that you could look at these and see which is which? You had to match them up. So that's mass spec. Again, we're only looking at sort of very predictable cleavage. We're not going to try to figure out what every little peak is. Let's look at this page here. Here are three mass specs. Here are three compounds. I know some of you have already been working on this. I'm not going to go over it today, but on Thursday we'll go over this, see how you did. Assign a compound to spectrum. 3 spectra, 3 compounds, match them up. Which goes with which? I would start by predicting fragments over here. Just writing them out with the masks. And then you predict 2 or 3 here. Well, then look over there and see which one contains the 2 or 3 that you predicted. So give that a try. Any questions about that? The next page, this is an example of a GC mass spec. You're doing GC mass spec in lab this week. Gas chromatography is often coupled with mass spec. Gas chromatography is generally similar to TLC, which you did in lab, except that was just on a little thin layer of silica gel. Gas chromatography is actually a big, expensive instrument. The compound mixture is injected, and the compound goes across a long wire loop that has some type of stationary phase in it. TLC, your plate was like this long. GC, you inject it, and it goes this wire that's like 20 yards long. It goes through there, so it has a long race to run, and things can separate as it moves through there. The mobile phase is not an eluate like hexane, but instead it's a gas. That's why it's called gas chromatography. But it's very automated, inexpensive to have one. You get a chromatogram that's put out, and you get peaks. The area under the curve relates to percentage of the component. This was from the some research, and it ended up being 4 components, with this one being major. Each component is then sent to the mass spec once they're separated on the GC column, and you can get a mass spec. And below is the mass spec for each, labeled A, B, and C. This particular one, there was no mass spec of this guy over here. I'm not sure what that is. The reaction we were doing is we were taking this here and fluorinating it, putting fluorine on, doing the reaction, and then running the GC mass spec. And it showed that the predominant was still starting material, nothing happened, but we did get some that had 1 fluorine on. Very interestingly, we found some that had 3 fluorines on. So look at the mass, added up 293. One of these mass spectra does indicate 293. And of course, there was other spectroscopy that went into this to confirm that it was indeed that structure, like NMR, etc. Question?
Why would one with 1 form and then 3 fluorines and not 2?
Because the first one goes on by substitution, replacing the H with an F. But then from there, you've got this alkene. And at that point, there's no way to add just 1. Because if you add 1 here, what are you saying you're going to add here? H? Well, you could. You could get rid of that and have H and F. But there's nowhere for that H to come from. It's almost like you did a substitution, and then you almost essentially added F2 across the pi bar. So you did a substitution, then you did essentially an F2 addition. We published a paper on that, getting the trifluorinated. We actually figured out conditions where this was formed in much greater percentage than these. And we also figured out conditions where only this was formed. This was just one of the GC mass specs that showed a good mixture. Of course, if you get a pure compound, you don't want it to look like a mixture. And on the back page is GC mass spec a pure compound, or at least what appears to be a pure compound. I have no evidence that it's impure. And until I find evidence that it's impure, I'm going to call it pure. See, the GC mass spec just shows 1 peak, like a TLC just showing 1 spot. Does that mean that 100% that it's pure? There could be 2 things under here that have the same retention time. And then the mass of that is 337, and then I got a mass spec that supports that molecular ion. You could maybe interpret some cleavage. A lot of times you're just looking for the base mass. I mean, this just supports it. Because the starting material had a very different mass of like 210. This supports this structure. That's actually called a fluorine ring system, spelled with an E, not an I. In organic 2 in the lab, if you take me, we'll make compounds like that, fluorine ring system, in a multi-week lab. So that's a nice looking GC mass spec. 1 nice peak supports the idea that it's pure. 1 component. So that's GC mass spec coupled together. A couple of miscellaneous things. Current advancements, they're doing mass spec of pills. Instead of dissolving it and then injecting it with a syringe, they're apparently just holding the pill up to there and letting it just pull some of the pill in. Things are getting very automated and very easy. And on the front goes, they're detecting cancer using mass spec. Probably there's some particular type of biomarkers when there's cancer around, and you can detect those molecules by mass spec. And of course, if you watch like CSI, they always say, you know, they got this drug sample with the blood, and they're like, I got GC Mass Spec. Shows that, you know, hey, did you get GC Mass Spec? So it's good for analyzing mixtures because the GC part separates your compounds. And on the back, if you want to get a job, spectroscopy like this, analytical chemist, highly coveted in industry, like in the drug companies. They want people who can analyze their drug products, doing syntheses. So if you can do mass spec, if you know how to use the instruments, know how to troubleshoot the instruments, how to get data from the instruments, very important. That's an old job ad. There's plenty of them that come out all the time. We'll move on to substitution. Any last questions about mass spec? So you need to be doing some work. Work on that one page with the 3, and we'll see what type of questions come up. Any questions now, though? Okay. 2 major topics remaining in the course. Substitution reactions, which I'm going to start, and then elimination reactions. I've already sent you that handout as well. 2 major topics. There's only like 5 or 6 types of reactions in organic chemistry. One of them we did with alkenes. What were they called in general? Addition reactions. We added Br2 to the alkene, etc. Hydroboration. We added something to the alkene. Addition. Substitution, we're going to be substituting, replacing something. Okay, that's what substitution is. You can also do elimination, where you just remove something. You don't replace it, you just remove it. That's different. Then you have a couple other just general types of reactions. Those are really big 3. Now, substitution, elimination are very important, probably to me even more important than your alkene addition reaction. Sort of an opening look here. This is a synthesis of Allegra. Right here, going from 31 to 32 in the industrial synthesis, is an SN2 reaction. Substitution, nucleophilic, bimolecular. We'll see what that is. SN2. What's going on? The mesylate, the OMS, is being replaced by a nitrogen. Basically, this nitrogen is going to come in here and bond to this carbon and kick this off. And now all that's bonded to the carbon in place of that. So it's a substitution. We call it replacement reaction. That's more of a gen chem term. Here's an example of an SN2. It's also an alkyne hydration, which that same reaction is in your lab, pre-lab. Here are some warm-up questions. These are the types of questions we need to be able to do after substitution. We'll learn SN1 and SN2. This can be 2 different substitution mechanisms. Alcohol, obviously the OH has been replaced by the Br. So it's been substituted. Mechanism for that, we also have stereochemistry to consider. Hopefully after today you'll be able to do several of those right there. Get started. Okay, as always, the headings of my handouts are meant to be very informative. What type of substitution we're going to be doing? Nucleophilic. A nucleophile is going to be doing something. With alkenes, we did electrophilic addition. Because the thing the alkene reacted with was an electrophile. Here's the main reactant. It's going to react with our substrate. We're going to call it nucleophile. Hopefully you know the difference, right? What type of carbon is this chemistry going to take place in? Tetrahedral carbon. That means it's what hybridization? Yeah, this chemistry takes in sp3 carbons. Does it say trigonal planar carbon? No, it doesn't. Don't do this chemistry at trigonal planar carbon. Tetrahedral. Okay, general line reaction. We're going to have a substrate for the leaving group. Leaving group I call X here. X is typically halogen, but we're going to expand it to be other things. The leaving group, from now on I'll call it LG. We need to have a nucleophile. I've shown that generically. In the reaction, the nucleophile is going to replace the leaving group. And now it's replaced it. What type of carbon was the leaving group on? Tetrahedral. See? It's not on an sp2 carbon, it's on tetrahedral carbon. Nucleophile, typically, nucleophile is going to have a lone pair. Lone pair is going to be very important. Got to have a lone pair to react. The X group is going to end up with an extra lone pair. Very generically, I'm showing no charge there. We do an exact example. I'll make my leaving group a bromine. Nucleophile, have a hydroxide, minus charge. Replace the bromine with hydroxide. Now have this alcohol. Hydroxide bonds to the carbon. Instead of the bromine is Br minus. Charge balance. This is a substitution reaction. Possible mechanisms for our example substitution reaction. Two different ways to replace the leaving group. Okay. The first one I say SN1. We're going to do this two different ways. And then we're going to look at the two different ways and say which one looks most reasonable based on what we know so far. What we've learned so far in this course. Okay. Let's see. How can I show this? Somebody give me a suggestion. Just magic? What can I show? Electrons doing what? What do we want to do? Suggestion? By the way, if you haven't asked a question here, and you don't routinely ask questions, I want to encourage you to ask questions. Shout something out. I can hear from some of you guys who haven't said much. Suggestion, what do we want to do? What do we need to accomplish? This has got to leave. That's got to get on there. Mechanism means we want to show arrows to show electron movement. BR leaves?
Yeah.
Electron pair on BR what?
Like the arrow showed the bond of it, like going to BR and then the electrons on the oxygen to the carbon. And
You want to do this?
yeah.
So what does that arrow mean to you?
Shifts the electron to the bromine.
And what's it going to give?
Carbocation.
Carbocation plus what?
Bromine.
BR had 3 lone pairs. What does this mean to you? Now has 4. These electrons move on to bromine. What's charge of this species? What are you going to call this process? Can we call it anything? How about ionization? I mean, that looks like ionization, doesn't it? We made ion. I mean, I showed some electrons moving. I'm not saying this is correct. I'm showing anything. Did we accomplish anything? Look, we just made one thing we got to make. We showed right there, we got to make it somehow. This is one way to possibly make it. That's a possible mechanism to make that. This, it's like a cation. How are we going to make the other thing?
Keep the electron from OH to the
These two,
cation
what?
to attack the cation.
This does this?
No, the other way. The electrons.
What's wrong with that?
You're making the cation go to the electron.
Well, arrows show movement of electrons. There's no electrons here. These electrons do what?
Attack the cation.
And what would that give?
OH with 2.
That would give that. There you go. How many steps? I just showed a formation of both things. How many steps in my mechanism? Step 1 was called what? What's step 2 going to, what do you want to call it? How about nucleophilic attack? Oh, how about this? Attack, let's make it so we can make a statement here. Nucleophilic addition to carbocation. That's not as simple as just ionization, but that's what we did. Nucleophile added to carbocation. Why are we calling this a nucleophile? What are nucleophiles like? They don't like electrons. Electrophile likes electrons. Nucleophiles like nuclei. What is the charge of a nuclei? Positive. Why would this like a positive? It's minus. Nucleophiles are typically minus. Or neutral with a high electron density. Typically it's going to be electron. There we go. There's a two-step mechanism. Ionization followed by that. Do you like this mechanism? Do you like our intermediate? What intermediate did I form? Primary, cation. Do you like this? Good, bad? I thought we answered that before.
It's not that good.
Carbocation. Never form carbocations. Mass spec is okay. Not that good for mechanisms. This is pretty bad. That makes me not like this mechanism. The mechanism I just showed is an SN1. Why is it an SN1? Let's do a reaction coordinate diagram. Okay? Reaction progress, type of energy. Let's say we start here with our, what do you want to call this guy? Alkyl halide?
Yes.
That is an alkyl halide, right? Alkyl bromide. Do we have any intermediates? Carbocation. I'm going to show it high energy. Everybody agree? Yeah, because it's a cation. It's positive. It's an ion. What's the final product? Yeah, I'm not going to show. This is going to be tough to determine here. It's not like we're going from a pi bond to two sigma bonds. This is tough, but we're back to neutral. Okay? And it's going to look something like this, right? One intermediate. Which is the rate determining step, do you think? First one. Why? Highest activation energy. That's why it looks like it's the hardest. Once you get here, falling downhill back to there, it's not going to take much activation energy. Rate determining step is the first one. Thus, what's the relative rate of the second step? Fast compared to that. Okay, here's why it's called SM1. How many molecules, how many of the reactors, the two reactors, how many of those are involved in the rate determining step? Which one's involved in the rate determining step? That one. Is that involved in the rate determining step?
No.
Just that ionizing? Hydroxide is not involved here. It's called SN1 because it's unimolecular. Only one molecule is involved in the rate determining step. That's SN1. We'll say more about SN1. Let's look down below. Let's do this by SN2. Okay, the 2 maybe already gives you some information. What's another mechanism we could show for getting to those 2 products? Back bonding of what?
Well, we formed that carbocation.
Form the carbocation? I think I'm just going to show you this. How about if these electrons attack here and push the bromine off all at the same time? What does that arrow movement right there give? There you go. That right there gives that. Hopefully everybody sees that. Because what are we doing right here? These electrons bind to the carbon. Electrons now bind to the carbon. 1 lone pair bind to the carbon, 2 lone pairs remain. What does this arrow mean to you? Bromine is getting kicked off. 2 electrons going with it. Bromine now has 4 electrons. That's minus. There you go. How many steps in this reaction? 1 step. This is called concerted. Basically, the nucleophile is attacking at the same time the leaving group is leaving. Since it's 1 step, what would the reaction coordinate diagram look like? It would just look like that. There would be no energy well. This is just 1 reaction, 1 step. That's your activation energy. I mean, we could show this higher or lower. I'm not just trying to say which is more stable here. That's just 1 step. Which is the rate determining step? That step. How many of the substrates are involved in that step? Both of them. Since they're both involved, and we're doing a substitution by a nucleophile, what do we call this mechanism? SN2. I just illustrated an SN2. It's a concerted nucleophile coming in, kicking off the leaving group. We actually did that when we attacked the bromonium ion. The nucleophile came in and kicked off the bromonium. Question?
Yeah, so obviously the difference is based on like how stable the carbocation is. Is it only possible to experiment and say like whether the carbocation is stable enough to like support SN1?
I'd have to hear your question again.
So basically, I was saying that the difference between SN1 and SN2 is like basically whether it's concerted or not. So in other words, it's basically a question of how stable or tolerable is the carbocation.
Yeah, yeah.
So is the only way to like prove which is preferred like experimentally, and there observe trends, or?
Yeah, that's what we'll learn. We'll learn trends, and yeah, ultimately something may not fit our trend, but we'll learn trends. We'll also see other ways to evaluate what mechanism it was as we get into it, like stereochemistry. For example, when the nucleophile attacks and kicks off the leaving group, how does this attack?
Backside?
Backside. Yes. And on the other hand, if you attack a carbocation, how do you attack a carbocation?
Both sides.
Either side. Okay? So the stereochemistry is going to be, we've already got that foundation there. We're going to use that knowledge. Okay, let's see what's down here. Proving mechanism by kinetic studies. We may have already answered this. I may have got to put it up there. Okay, kinetic studies have shown that the rate of the above reaction can be affected by changing the concentration of either the alkyl bromide or the hydroxide. Either one. That means the concentration of both of them affect the rate. Thus, since the rate depends on both of them, each must be involved in the rate determining step. So you can tell what's involved in the rate determining step by changing concentrations. If it's involved in the rate determining step and you change the concentration, you're going to affect the rate determining step. If it's not involved in the rate determining step and you change the concentration, the reaction is going to say, who cares? that substrate is not involved in the rate determining step. The fact that both of them affect the rate, changes in both of them affect the rate, means that both are involved in the rate determining step. It means that this is SN2. Okay? Basically, just getting to the fact that if they're both involved in the rate determining step, concentration of both is relevant. Rate equation for this reaction. Always there's some type of constant for your reaction. That's just based on, you know, is it a secondary, how substituted it is, some type of constant. But then you also have concentration. If it's SN2, the constant's going to be multiplied by both substrates. The alkyl bromide and hydroxide. This is SN2. If it's SN1, only one of these would be in the rate equation. Which one would it be? Alkyl bromide. Okay, hydroxide concentration does not matter in an SN1. Reaction coordinate diagram, we already did that. Which mechanism matches the kinetic observations? SN2. This is the kinetic observations, SN2. The example reaction is SN2. Why? Because you're not going to want to make a primary cation. But I showed you the SN1 mechanism as well. Okay? SN1 we will use. We're going to concentrate on SN2 for a while. What type of substrates are better for SN1? Not primary, but tertiary. If that was a tertiary bromide, it'd be more prone to forming a tertiary cation. And the SN1 would be more favored. We will actually say that you don't do SN2 on tertiary aniline. Okay, we've got a long way to go. Stereochemistry. Okay, if we add a carbon here and make this original chiral, that's R, if we react this with KOH, hydroxide, we get a substitution reaction. Get this plus KBr. I included spectator ions, okay, that's hydroxide, this is Br minus. The outcome of this, I'm saying S only. Starting with R, we get S only. So the reaction is an antioselective. This is our first ever antioselective reaction. Now this is going to be optically active. How can that be optically active? Well, the starting material was. If the starting material is not, that counts. But here we got a chiral starting material. Now, because we only get S, we say that this reaction is known to give complete inversion. R to S only is inversion, complete inversion. Questions? Is an SN1 mechanism more or less likely for this reaction compared to previous? That has nothing to do with stereochemistry. What was the question? I mean the answer? It's more because it's secondary. It's a secondary halide. If that ionizes, we make a secondary cation. That's more likely than making a primary. Okay, this first question has nothing to do with stereochemistry. Okay, it's more likely because it would be a secondary cation. Okay, which mechanism, SN1 or 2, does the experimental evidence support? This is referring to stereochemistry. Why does it support SN2, T? We got complete inversion. Look back at your two mechanisms. If it's SN1, what do you form as an intermediate? Carbocation. Okay, let's consider the. Let's do it here. If that just ionized, we would get boom, boom. We would get this cation, right? If the Br minus just ionized off. Okay, what's the geometry of the cation? sp2, trigonal planar. It's flat like a piece of paper. There it is, okay? Here's the cation. Hydroxide attacks it. Is it going to attack from the front or back? Both. You would get one product. It would attack from the front. You would get that, and you would also get where it attacks from the back, and you would get that. This would be S, this would be R, and you would not expect only S, right? You would expect both S and R, front and back. But that up there says you get only S, so it can't be SN1. It's SN2. Because SN2, we know that whenever you attack a carbon and kick off the leaving group is back. Okay? If that's the plane, the bromine is back, right? And the dash going back. So how does the hydroxide attack? From the front. Comes in and kicks off the leaving group. Now the hydroxide's forward. That stereochemical outcome indicates SN2, not SN1.
I'm just curious why, like, it just kind of shoves the H over to where the BR used to be.
The H here is forward. Yeah. The H here is forward.
And it doesn't end up kicking the
Yeah, we kind of showed that before. Here's the plane. The H is forward. The bromine is back. The H is forward. Okay. Pretend the plane is still here. When the hydroxide comes in, it comes in. I'm going to try to kick this off. It comes in and pushes it back. It does. It is now back. If you look up inversion, Walden inversion, it sort of talks about that. We'll actually look at this transition state of how things go from forward to planar to back. Sort of like an umbrella that gets inverted in the wind. That has ever happened. Typically, the umbrella's like this over your head. Sometimes it can go up like that. Okay. But on the way, there's a planar point where it's all planar before it goes the other way. We'll talk more about that. Introductory, though, the stereochemical outcome indicates SN2, backside attack with inversion. SN1 doesn't give inversion. It gives, what do you want to call it when it gives both S and R? This would be a 50-50 mix.
Racemic.
Racemic. SN1 gives racemic. That transition state I talked about, looks like it's time to show it. How is inversion obtained? Let's see if we can draw the transition state. See if I can do it without looking at my notes. If I can get the bonds right. Let me draw the transition state. I'm drawing this here. I'm drawing the transition state. We're going to have a bromine leaving. We're going to have a hydroxide coming in. Let's see. I think I want to draw. I'm about to come over here so I get the R and S right. Let me make the bromine. Here's the carbon. We'll put the bromine here. We're going to come this way. The bromine's there. Don't write it yet. Let me make sure I get R here. If you do that, there's an ethyl. There's a methyl. There's an H. We got a carbon with a bromine, an ethyl, a methyl, and an H that's undrawn. This is it. Is this R? Let me see. H in the back. Bromine. No, that looks like S. Instead, I'm going to erase this and make this be the ethyl. So I got a carbon with a methyl. Bromine is here. No, we're going the other way. No, I had it right to begin with. That's right. Bromine, if I'm up here, bromine's at 6 o'clock. The ethyl's at 9. The methyl. That's R. Okay, that's R. That's what we got up there, just drawn differently, but it's R. What do we got here? Hydroxide. If the bromine is that way compared to the carbon, where does this come in from? Completely 100 degrees opposite. That's called backside attack. So this comes in here. As this comes in, what starts happening in the transition state? This bond is starting to be made. So I'm showing the bond starting to be made. And then this gets kicked off. But as it's getting kicked off, what's happening? It's starting to break. So this is the bond making, that's it breaking. This is minus, that's neutral. This point it's partial minus because it's like starting to bond. Once it fully bonds, it's going to be neutral. Once this continues on, what is this going to become? At this point, it's partial minus. As it continues, it's going to become full minus. And at this point, we have H, we have ethyl, and we have methyl. But these are eclipsed. Those are supposed to be right in front of each other. Okay? What we got is, pretend my arm is the bromine bond. Everything else is sort of that way. Okay? Now hydroxide comes in. When it comes in, it makes all this go flat and planar. And this is supposed to be all just one plane with that behind it. Now as the bromine gets kicked off, what happens? This stuff actually comes this way. I can't get in my hand. But we end up with a carbon here. This stuff comes this way. Like this. This is not drawn. Let me draw this a little bit different. That's sufficient. It just doesn't look good to me. We want the ethyl. The ethyl's still going to be molded. Like that. That's R. This should be S now. Do it. OH. No, yeah, that's S. Get inversion. Here's your transition state, or activated complex. Okay? It's not an intermediate. It's a transition state, activated complex. It's the thing, you know, when we do like this, it's the thing that's the high energy thing. It's not an energy well. It's not a discrete intermediate. Important thing here is this is sp2-like. The three groups are planar. Trigonal planar. The H, the methyl. What's left over on sp2 atom? What other type of orbital? A P. And it's perpendicular to that plane. Look here. Almost looks like a p orbital there that you could draw there. Important things here is when it's sp2, What's the bond angle between these two groups here? The bond angle. It's coming off this carbon here. 109.5. What's that carbon tetrahedral? 109.5 bond angles. In the transition state, what's the bond angle? Okay, they're in front of each other, but it's still there's a bond angle between them. What is it?
20.
Yeah, 120. Does sp2 like? That has consequences of maybe you have a substrate where these two cannot spread out to 120. If they cannot spread out to 120, it means it can't achieve this transition state. And if you can't do that, the reaction is going to be very tough and may not occur at all. So understanding the geometry, what the transition state looks like, helps you predict some reactivity. Okay, questions about this?
You said that it might not be able to spread out to 120 for some reason? Like,
right.
Like what would not be able to spread out to 120?
Some type of ring where we really need to move on. Just sort of giving you, might be a question in the workbook that relates to that. Okay. Look in the workbook, see, maybe ask after class or next time. We can see if something comes up. Maybe we'll refer back to it in another day or two. Okay. Other questions about the transition state? Does this make sense how the hydroxide's partially bonding and the bromine's partially breaking? That okay, from here for a while, in the handout we're going to look at the different characters or actors that are involved in an SN2 reaction. Question?
Yeah, why is it 120 degrees even when they're eclipsed?
Well, just because they're eclipsed doesn't mean you can't have bonding. Are my fingers eclipsed to you?
Oh.
Are they?
Yeah.
Okay, but see how the bond angles can change? So here it's got an angle of like 30 degrees. What is it now? You couldn't see because it's eclipsed.
Okay.
But that can change. You guys can see it. But to her, they're eclipsed. They're in front of each other. But it can still be a bond angle. See, now it's eclipsed to them. See, the bond angle still can change. Well, it's sp2-like
Is 180 going to be eclipsed?
for a variety of reasons. It looks like that p orbital there, perpendicular to the plane. But the three groups in that plane have bond angle of 120 degrees.
Look at it dead on.
Okay, the different actors in an SN2 reaction, nucleophile. If the nucleophile reacts with the alkyl halide, what can we also call the alkyl halide?
Electrophile.
Electrophiles, yeah. You know, nobody asked me back when the hydroxide attacked the, why would this be attracted to that carbon? It's very simple, but we never really just stated it. Yeah, we do have a dipole here. It does have slightly positive. But it's not a carbocation. So, I mean, typically to get this to attack, it does take a little, like, heat, time. But there is some partial positive here. Otherwise, it wouldn't be attracted to it. Okay? Okay, let's look at reactivity of the various electrophiles. This is the substrate with the leaving group. First thing is the effect of a p orbital immediately adjacent to the reaction site. And I can't believe I did it, but I left up the transition state. Usually I erase it. I have to redraw it. If you have a p orbital adjacent to the reaction site, it makes the reaction very easy. Why? Well, look at my transition state. What am I saying? Let's say that the carbon next door had a p orbital. It doesn't in this example, but let's say it does. Let's put one next door. Why would a p orbital next door stabilize the transition state? Because you can get p orbital overlap in your transition state. Because remember, in the transition state, this essentially is like a p orbital. And if you got a p orbital next door, p orbitals can overlap, and that's a stabilizing thing. And if you stabilize your transition state, is that going to make the reaction easier? Yeah. That's how you make reactions easier. You make the transition state easier to achieve. If it's lowered energy, it's going to be more easy to achieve. Look at all these here. I'm going to erase this now. All these chlorides are very reactive in SN2. Why? Well, I'd be careful about calling it resonance. I mean, there's no, that's an sp3 carbon. It doesn't participate in resonance. But what's next door? Here, what's next door? What's next door? What's next door? It's actually two here. And when the hydroxide or nucleophile attacks here, what type of geometry does this carbon take on? sp2-like with a p orbital. You get a p orbital in here of the nucleophile where it's bonding and breaking. It looks like they're bent or away from each other, but this can overlap with the adjacent one and stabilize that transition state. All these are examples of that. All of these here undergo SN2 very easily. Because of that, they're all very toxic. Because you get them in your eye where you have lots of nucleophiles, like amines and stuff, and they'll just react. You'll end up going blind. Or other places. These are all very reactive because of that. Transition state, very easy. They're all much more reactive than, say, this. No p orbital. There's not any of that stabilization. World Series just ended, right? Back in the 90s when the Braves were in the World Series, a long time ago. Anybody know what this is? Well, get rid of that. That's ethyl chloride. Anybody know what ethyl chloride is used for in baseball? You ever seen someone foul a foul ball off their foot and they do it, and the trainer comes out and sprays something on it? Yeah? What do they spray on? Ethyl chloride. Why? Because it's a gas, and when it comes out, it quickly volatilizes, and it numbs. It creates coldness. Okay? Ethyl chloride. Tell me again. Okay, let me finish this good yarn of a story here. Ethyl chloride is not that toxic. It can undergo an SN2, but it's going to take kind of heating with a long reaction time. You would never spray this on somebody. You're going to kill us all. Okay? This is too reactive. Why? I already told you why 3 times. Also, if you go back and look at the tape of the World Series, you remember Tim McCarver? He used to call the games. He used to be a catcher for the St. Louis. But Tim McCarver, anybody old enough to remember Tim McCarver? Well, he said that the guy's coming out and he's going to spray ethyl chloride on him. He called it ethyl chloride. All right, guys, y'all have a good night.